Our research topic is analyzing the carbon footprint of state-of-the-art large language models, calculation methods and sustainable solutions. According to the reading, one must initially understand the distinction between the correlated concepts, which are sustainability for AI and sustainability of AI. There was frequent research on sustainability for AI, but it failed to account for the environmental impacts caused by the development of AI. Thus, this shows the sustainability of AI should be prioritized. Researchers should then decide whether using the particular sustainable AI would account for society's needs and not pose a threat to ethical norms, considering the fact that using AI is a choice. When defining the scope of the carbon footprint estimation, the entire cycle of the model includes stages such as data collection, model development, training, and interference. Even though training data using renewable energy or carbon offset resources seems like a viable solution, challenges arise due to limitations in renewable energy infrastructure and availability. Information must be gathered regarding the training duration, data center location, machine type, and more, in order to calculate the total energy consumption. Once that is established, there are three possible tools for calculating carbon emissions: Experiment Impact Tracker, Machine Learning Emissions Calculator, and Carbon Tracker. However, we will use the Machine Learning Emissions Calculator. The reason we cannot use Experiment Impact Tracker is because it requires monitored energy usage observations at specific intervals for the purpose of more precise calculations. However, since we do not have the existing data nor can we manually measure for this, we cannot utilize this method. Similarly, the reason we cannot use the Carbon Tracker tool is because it utilizes the CPU, which incorporates data movement, model architecture, and optimization techniques. And these are beyond what we can obtain. This part is an explanation of the calculations. For instance, with a GPU consuming 250 watts of power and being used for 100 hours, which results in 25,000 watt-hours of energy consumption, and it is assumed that hardware type and cloud region the compute took place has no effects on the calculation. After that, analyzing the energy sources used in data centers, such as coal-fired power plants versus renewables, helps quantify the environmental impact. If data center primarily relies on renewable energy sources with a very low carbon intensity, emitting only 0.05 kilograms of CO2 per kilowatt-hour, calculating the energy consumption of carbon intensity with energy consumption by multiplication. 25 kilowatt-hour times 0.05 kilograms CO2 over kilowatt-hour equals 1.25 kilograms CO2e. In other case, if one relied on the coal-fired power, then carbon intensity would be summed up to 0.9 kilograms, resulting in 90,000 kilograms of CO2. These calculations comply with the necessity of ethical safeguards and supporting the carbon emissions reports as mentioned in Sustainable AI Principles. They allow a more reliable estimate of the carbon footprint in the case of training language models. A proportionality framework should be also made to assess whether the resources expended in training an AI model for a specific task align proportionally with the carbon footprint and environmental impact related with such activities, supporting the goal of minimizing environmental impacts while maximizing societal benefits altogether. Therefore, when a researcher includes these principles into the numerical calculation process, he prioritizes sustainability and mitigate emissions effectively. So what do we recommend to reduce the carbon footprint from training large language models? Efficiency and optimization are two factors that can help reduce energy use. There are energy-efficient hardware which offer higher performance per watt, thereby reducing energy consumption during training. Also, opting for renewable energy in this process would be sustainable. Optimization methods such as model pruning, where less important parameters of the model are removed, will result in less energy consumption. And finally, Optimized algorithms allow for computations to be focused on the most relevant parts of the model, while ignoring the less important parts. In conclusion, these methods can aid the process of training large language models while also benefiting sustainability. Although we cannot, and in many ways should not, prevent the development of such resource-heavy models, we can focus on improving our methods for a more sustainable future. Thank you for listening.